Hey everyone! Welcome back to part 2 of our leaf disease detection using deep learning project. In the previous video, part 1, we worked on the entire data preparation process. We collected our leaf disease dataset, pre-processed and normalized all the images, split them into training and validation sets, and even visualized a few healthy and diseased leaf samples. So, if you haven't seen that yet, make sure to check the link in the comments before continuing. It'll help you understand this part better. Now, in today's session, part 2, we'll move to one of the most exciting steps, model building. We're going to design 3 different CNN-based models using transfer learning. We'll build a custom VGG16 model, a VGG19 model, and finally, an EfficientNetB4 model, which is both lightweight and powerful. Each of these models will be trained later to detect various leaf diseases automatically. Alright, enough talk. Let's dive into the code and start building our models step by step. Make sure to follow along with me, because I'll explain each model clearly so you understand why we're using it and how it works. Define input shape and number of classes. Here we define the input shape and number of output classes. For our deep learning model, the input shape specifies that each input image has 3 color channels and is resized to a uniform dimension. The variable number classes equals 26 tells the model that there are 26 distinct categories of leaf diseases to classify. The model is now configured to accept RGB images of a fixed size and predict one of 26 possible disease classes. Build and compile custom VGG16 model. In this section, we build a custom deep learning model using the pre-trained VGG16 architecture. We load VGG16 with ImageNet weights and exclude its top layers to fine-tune it for our leaf disease dataset. All the pre-trained layers are frozen to preserve their learned features. Then we add new layers, global average pooling 2D, 2 dense layers with batch normalization and dropout for better generalization, and finally a soft max layer for multi-class classification. The model is compiled using the atom optimizer and sparse categorical crossentropy loss, tracking accuracy as the evaluation metric. The model summary displays the complete architecture, showing the VGG16 base, followed by custom layers, confirming successful model construction and compilation. Training the customized VGG16 model. This code trains the customized VGG16 model using the training data xtrain and ytrain for 10 epochs with a batch size of 64. During training, it evaluates the model's performance on the validation data after each epoch to monitor accuracy and loss. The fit function returns a history object containing training and validation metrics, which is stored in VGG16 pre-trained for later analysis or visualization. After execution, the model becomes trained on the given dataset, and VGG16 pre-trained stores the training history, including epoch-wise loss and accuracy values for both training and validation sets. Plotting training and validation performance of VGG16. This code defines a function plot history that visualizes the model's training performance over epochs. It takes the training history object and a title as inputs. Inside the function, 2 subplots are created, one for accuracy and another for loss. The first plot shows how the training and validation accuracy change across epochs, while the second shows the training and validation loss trends. Finally, the function plot history is called to display the accuracy and loss curves for the VGG16 model. 2 side-by-side graphs appear, the left one showing the model's accuracy improvement over epochs, and the right one showing how the loss decreases helping to evaluate the training and validation performance of the VGG16 model. Evaluating the VGG16 model performance. This code evaluates the trained VGG16 model on both test and training datasets. The evaluate function calculates the loss and accuracy for each dataset. First, it computes valid loss and valid ACC using the test data to measure how well the model performs on unseen data. Then, it computes train loss and train ACC on the training data to check how well the model learned during training. Finally, the results are printed to display the validation and training accuracy and loss values. The console shows 4 outputs: validation accuracy, validation loss, train accuracy, and train loss, allowing you to compare training and testing performance and identify if the model is overfitting or generalizing well. Testing the final accuracy of the VGG16 model. This code evaluates the trained VGG16 model on the test dataset to measure its final performance. The evaluate function returns 2 values, loss and accuracy. After evaluation, the model's accuracy is printed in percentage format using the line print, which rounds the result to 2 decimal places. The console displays the model's final test accuracy as a percentage, showing how well the VGG16 model performs on unseen data. Visualizing model predictions with a confusion matrix. This code defines a function plot confusion matrix that visualizes how well the VGG16 model classifies test data. The function first uses model.predict to generate predicted probabilities for each class, then converts them into class labels using np.argmax. It compares these predicted labels with the actual y-test labels using confusion matrix to compute the count of correct and incorrect predictions. Finally, it plots the results as a heat map using Seaborn, where rows represent actual classes and columns represent predicted classes. The function is then called with the VGG16 model and test data to display the confusion matrix. A confusion matrix heat map appears, showing the number of correct and incorrect predictions for each class. Darker diagonal cells indicate more accurate predictions, helping to visually assess which categories the VGG16 model performs well on and where it misclassifies. Generating the classification report for VGG16 model. This code evaluates the VGG16 model's performance in detail by generating a classification report. First, VGG16 custom model.predict produces predicted probabilities for each class in the test set. The line np.argmax converts these probabilities into predicted class labels by selecting the class with the highest probability for each sample. Then the classification report function compares the predicted labels with the actual labels y-test and prints precision, recall, F1 score, and support for each class, using the given category names for better readability. The console displays a detailed table showing each class's precision, recall, F1 score, and overall model accuracy, helping to understand which categories the VGG16 model predicts accurately and where it needs improvement. Building and compiling a customized VGG19 model. This code builds a transfer learning model using the VGG19 architecture pre-trained on ImageNet. It first imports the necessary Keras and TensorFlow modules and loads the VGG19 base model with include top equals false to exclude the default classification layers while keeping the pre-trained convolutional layers. All base layers are frozen to preserve the learned features. On top of this base, several custom fully connected layers are added: a global average pooling layer, 2 dense layers with ReLU activation and dropout for regularization, and a final softmax layer that outputs predictions for the number of target categories. The model is then compiled using the Atom optimizer with a learning rate of 0.0001 and sparse categorical cross-entropy loss for integer-labeled data, tracking accuracy as the performance metric. Finally, modified VGG19 model.summary displays the full architecture and parameter details. The console shows a detailed model summary, listing each layer, its output shape, and the number of trainable and non-trainable parameters, confirming that the VGG19 base layers are frozen and the custom classification layers are ready for training. Training the customized VGG19 model with early stopping. This code trains the modified VGG19 model on the training dataset for 10 epochs with a batch size of 32. The validation data argument uses to monitor model performance on unseen data after each epoch. An early stopping callback is included, which stops training if the validation loss does not improve for 5 consecutive epochs and restores the best weights to prevent overfitting. The training process returns a history object that contains epoch-wise metrics such as loss and accuracy for both training and validation, allowing visualization and analysis later. The model is trained on the dataset with early stopping to prevent overfitting, and the history object records the training and validation accuracy and loss for each epoch, which can be used for plotting learning curves. Saving the trained VGG19 model. This code saves the trained modified VGG19 model to a file in HDF5 format. The save function writes the model architecture, weights, and optimizer state to the specified path, allowing you to reload and use the model later without retraining. In this example, the model is saved to Google Drive at Content Drive, My Drive, New Projects, P5 Modified VG19 Modeled H5. The model is successfully saved to the specified path, making it easy to load later for inference, evaluation, or further training using tf.keras.models.loadModel. Plotting training and validation curves for VGG19. This code visualizes the training performance of the modified VGG19 model over epochs. 2 subplots are created side by side. The first shows the training and validation accuracy curves, while the second shows the training and validation loss curves. By plotting history.history and history.history, you can observe how accuracy improves on both training and validation sets. Similarly, history.history and history.history show how the loss decreases during training. 2 line plots appear, one for accuracy and one for loss, helping to assess model performance, check for overfitting, and visualize how well the VGG19 model learned from the dataset over time. On the left, we see the accuracy curves of the modified VGG19 model. The blue line represents training accuracy, and the orange line represents validation accuracy. As the epochs progress, both lines rise, showing that the model is learning and generalizing well. On the right, we see the loss curves. The blue line is training loss, and the orange line is validation loss. Both curves decrease over time, indicating that the model is minimizing errors. By comparing these curves, we can check for overfitting or underfitting. If the validation curves closely follow the training curves, it means the model is performing consistently on unseen data. Overall, these plots visually summarize how well the VGG19 model learned from the dataset over the training process. Evaluating the modified VGG19 model. This code evaluates the trained VGG19 model on both the test and training datasets. The evaluate function calculates the loss and accuracy for each dataset. First, valid loss and valid ACC are computed using the test data to measure the model's performance on unseen data. Then, train loss and train ACC are computed using the training data to check how well the model learned during training. Finally, The results are printed to display validation and training accuracy and loss. The console shows 4 outputs: validation accuracy, validation loss, train accuracy, and train loss. This allows comparison between training and testing performance to identify if the model generalizes well or is overfitting. Testing the final accuracy of the modified VGG19 model. This code evaluates the trained VGG19 model on the test dataset to measure its final performance. The evaluate function returns the test loss and test ACC. The accuracy is then printed in percentage format using print, which rounds the result to 2 decimal places for clarity. The console displays the final test accuracy as a percentage, showing how well the modified VGG19 model performs on unseen data. Visualizing predictions with a confusion matrix for modified VGG19. This code defines a function plot confusion matrix to visualize how well the modified VGG19 model classifies the test dataset. It first predicts class probabilities using model.predict and converts them into predicted class labels with np.argmax. Then it computes the confusion matrix by comparing the predicted labels with the true labels y-test. The confusion matrix is displayed as a heat map using Seaborn, where rows represent actual classes and columns represent predicted classes. Finally, the function is called with the modified VGG19 model to display the confusion matrix for all categories. A heat map appears showing correct and incorrect predictions for each class. Diagonal cells indicate correct predictions, while off-diagonal cells highlight misclassifications, helping to identify which categories the model predicts well and where it struggles. This confusion matrix visualizes how well the modified VGG19 model predicts the test dataset. Each row represents the actual class, and each column represents the predicted class. The diagonal cells show correct predictions, while the off-diagonal cells indicate misclassifications. By examining this heat map, we can see which categories the model predicts accurately and which categories it struggles with. This visual helps us understand the strengths and weaknesses of the model's performance across all classes. Generating the classification report for modified VGG19. This code evaluates the performance of the modified VGG19 model on the test dataset in detail. First, modified VGG19 model.predict generates predicted probabilities for each class. The line np.argmax converts these probabilities into predicted class labels by selecting the class with the highest probability for each sample. Then classification report compares the predicted labels with the true labels y-test and prints precision, recall, F1 score, and support for each class, using the provided category names for clarity. The console displays a detailed table showing each class's precision, recall, F1 score, and support, along with overall accuracy. This helps assess which categories the model predicts accurately and highlights areas where it may be underperforming. Installing the EfficientNet library. This command installs the EfficientNet library in your Python environment using pip. The flag stands for quiet, which suppresses most of the installation output. EfficientNet provides pre-trained convolutional neural network architectures that are optimized for both accuracy and efficiency, making them useful for image classification tasks. The EfficientNet library is installed and ready to use in your code, allowing you to import its models for transfer learning or training custom image classification models. Building and compiling a customized EfficientNetB4 model. This code creates a transfer learning model using the EfficientNetB4 architecture pre-trained on ImageNet. The base model ENet is loaded without the top classification layers to allow custom layers for your dataset. On top of the base, a global max pooling 2D layer is added to reduce the feature maps, followed by a dense layer with 256 units and RealU activation. Batch normalization and dropout are included for regularization. The final dense layer uses softmax activation to output predictions for the number of classes. The Model E Model B4 is compiled using the Atom Optimizer with a learning rate of 0.0005, sparse categorical crossentropy loss for integer labels, and accuracy as the evaluation metric. The EfficientNetB4 based model is ready for training on your dataset. You can now fit it on training data and use it for evaluation or prediction, leveraging the pre-trained features of EfficientNet for better accuracy. Perfect! So today we've successfully defined our model input shape and number of classes, built 3 transfer learning models, VGG16, VGG19, and EfficientNetB4, and compiled them, ready for training. So now our models are completely ready to learn from the dataset. In the next part, we'll cover model training, train VGG16, VGG19, and EfficientNetB4 on the Leaf dataset, and fine-tune them for accuracy, performance visualization and testing, plot accuracy loss curves, and test all models on unseen Leaf images. Model comparison and results. Compare all 3 models side by side and identify the best performing one. If you enjoyed this session, make sure to hit the like button, drop a comment if you're following along, and subscribe for the next part of this series. And if you're stuck anywhere, just comment below. I'll try to help you out. See you in the next video, part 3, where we finally train and test our models.